Okay, so it's 3-5. Let's start. Uh, if others join, they will join later. So let's start. So good afternoon. Welcome to the third week of discussion session of the course Finite Element Method. Myself, Asif. I am a PhD scholar from Department of Civil Engineering, IIC Bangalore, and the course instructor of this course is Professor Vishwanath Banerjee and Professor Amit Shah. Uh, okay, before going through this week of discussion session, I would like to clarify the last question which we discussed in the last week. Uh, that was like the 11th question. So this was the question. So we were not getting the solution. So I worked it out and I got that the question needs to be corrected. The question need to be modified is in this way that d by dx need to be taken out and it should be d by dx. This should be the governing equation. D by dx as a whole 2 plus x square times du by dx equal to 0. So if we apply this and then as we were solving the question earlier like multiplying with the weight function, then using integration by parts and expanding the term, then uh, substituting the approximation function and the weight function what we are given with and simply solving, so we'll get the solution which we wanted. So this will be this needs to be corrected. So I think uh, please note it down this thing, Abraham. Okay,
Okay, sir.
yeah. And one more thing to ask that you have got the link for the notes as well as for videos, right?
The first week link is given.
Okay. So second week lectures
Not
like
yet.
okay, it will be provided too. Okay. Okay. Now let's move on to the discussion of this week's. Okay. So here is the first question. Let a differential equation is uh, p second derivative of phi plus q first derivative of phi plus phi equal to f for domain is from 0 to 1. Consider p, q and f as the known function of x where phi is a field variable. If v is a weight function, the weighted residual statement is. So what do you think is the correct answer?
It's C.
Yes. Yes, the correct answer is C. And how do we get this is we have the differential equation as given already. P d2 phi by dx square plus q d phi by dx plus phi equal to f. So this differential equation, if my phi is an actual solution, this governing differential equation will be satisfied at all points. Yeah, Rafael, do you want to ask anything?
No, I just
Uh,
wanted to say
okay,
hi.
yeah, yeah, hello. Okay, so as I was saying, if phi is my actual solution, this governing equation will be satisfied throughout the domain, like at every point of this domain. And if my phi is an approximate, this need not be uh, uh, an exact solution. So like p d2 phi dx square plus q d phi dx plus phi minus f need not be equal to 0. if phi is not my exact solution. So this is what we call it as my residue. Like if my phi is not my exact solution, this will give me some values, and that is called a residue. So when we multiply in weighted residual method, what we do is we multiply this residue with weight function and integrate it over the domain and take it equal to 0. Like weighted residual state method says, we satisfy this governing differential equation in a weighted sense. Did not satisfy at every point, but this should satisfy throughout the domain in a weighted integral state sense. Okay, Rafael is saying, could I ask you questions about lectures today if you will have time? Yeah, sure. After we finish this week's questions, then we can have a doubt session also. Okay. So we have this. Now just substitute this into this. We'll have p d2 phi by dx square plus q d phi by dx plus phi minus f 0 to 1 dx equal to 0, and this will be equal to 0 to 1 vp d2 d2 phi dx square plus vq d phi by dx plus v phi minus vf dx equal to 0, and according to the options it is given as q d phi by dx plus v phi dx equal to 0 to 1 vf dx. Right? So correct answer is option C. Okay, so let's move on to the next question. Choose the correct option from the following statement. In weighted residual method, the weight function must satisfy homogeneous boundary condition. Second statement is, in weighted residual statement, the residual of a system can be orthogonalized with respect to weight function. So what will be the correct answer? Yeah, Rafael, you can answer.
I believe both will be correct, because weighted residual statement as a statement, it does not require it does not require it is not required to satisfy a homogeneous boundary condition. For instance, Petrov, the first method, Galerkin Petrov, does not require homogeneous boundary conditions, because we can choose x1 and x2 as we did in lectures.
Yeah.
But weighted residual statement also can be orthogonalized in the sense that we are writing weight functions, and the meaning of this function is orthogonalizing with respect to some weight function.
Yeah.
The meaning. So it's a
Yes.
dot product.
Yes, you are absolutely correct. So correct answer is option B. As just I showed you, like this is what a weighted residual statement says: 0 to 1 v to r dx equal to 0. This is kind of the statement which talks about the orthogonalization. The residual of a system can be orthogonalized with respect to a weight function. So this shows that this is second statement is correct. And as Raphael told that first statement is not correct, because weight function need not satisfy homogeneous boundary condition. In that, I must add, like weight function like should satisfy homogeneous essential boundary condition. That is what is required in like Petrov-Galerkin method. Bubnov-Galerkin method. So with that, like only second statement is correct. So okay, let's move on to the next question. So the third question is, choose the correct option from the following statement. First statement is Galerkin method requires higher differentiability than Rayleigh-Ritz method. Second statement is, unlike Galerkin method, differentiability is transferred in weight function through the integration by parts. In case of Rayleigh-Ritz method, so options are, first statement is only correct, second statement is only correct, third option is both are correct, but second is not the correct explanation of first statement, and fourth option is both are correct and second is the correct explanation of first statement. So Rafael wants to answer. Yeah, Rafael.
Can I answer this question?
Yeah,
Try to
sure.
answer.
Yeah.
Galerkin as a method itself is not require a higher. It is require higher differentiability because, as a lecturer said, we can use Galerkin method without integration by parts. So it requires higher differentiability because in Galerkin method we are not doing differentiation by parts. So in Rayleigh methods, however, it requires integration by parts, so requirements for differentiability is less in Rayleigh-Ritz method. The Galerkin method, the correct options here is both are correct, and the second is correct explanation to the first. But
Yeah.
it is not clear here. Is a question I should notice that what does it mean differentiability is transferred? My understanding is here that differentiability just because it requires the function that is in the weight statement, the differentiability requirements is less than in the original weak statement. So the meaning of the words is transferred is not clear here.
Okay. To make it clear, I'll just say, uh, suppose for a bar problem, we have the Gaussian differential equation is like this, right? Now, if we see, this is the Gaussian differential equation for a bar problem. Here, if we see the equation, we can say for certain that you need to have a second order derivative, second order differentiability. Then only this differential equation can be satisfied. But uh, but what happens in Rayleigh-Ritz method is this is like, this is for a strong form, right? For in Rayleigh-Ritz method, when we convert it to a weak form, suppose we multiply it with a weight function v dA d2u by dx square plus q, integrate it over the domain. Okay, so weak form, this would be using integration by parts. We get 0 to L V. Okay, this will be VEA du by dx at the boundary, then 0 to L dV by dx EA du by dx plus 0 to L VQ dx equal to 0. This can be further simplified. So if you see this weak form, here the differentiability requirement for our solution is only first order differentiability. and the like earlier it was second order differentiability requirement. Now that has been transferred to my weight function. This is what the second statement says, like differentiability is transferred in weight function through the integration by parts in case of Rayleigh-Ritz method. So yeah, so as Galerkin method does not require integration by parts, it needs like higher differentiability. It requires higher differentiability. While in Rayleigh-Ritz method, where we use integration by parts, we transfer the differentiability to the weight function. So the differentiability requirement for our solution reduces. So both statements are correct, and the second statement is my correct explanation for my first statement. So I hope this clears. Okay.
Yes, thank you. It's clear.
Yeah. Okay. Let's move on to the next question. So next question is let phi and v are approximation and weight function respectively in a weighted integral form of a system. The correct option corresponds to the choice of v is, and these are options pertaining to Petrov-Galerkin and Bubnov-Galerkin method. So what do you think? What would be the correct answer? Question for answers. So anyone can guess? Yeah, Rafael, you do have. I'll ask Abraham first this time. Abraham, if you know, can you?
Sir, actually, I got the answer from the solution, but I don't know the reason. I know it's option A, but
No,
actually, I
no.
don't know how. I mean,
Option B.
yeah, that exactly. But I don't know the reason. I got it from the solution.
Okay. Okay, Rafael, do you have any insights to provide us?
Yes, thank you. The beer is correct answer. The reason of that is because when we write weak form as a dot product between weight function and the residual, we can choose between options to choose this weight. We can arbitrary by some reasoning choose as this weight function, and just to be just we need to create the we need to create a linear algebraic equations to find these weight functions, and arbitrary it's just a method that we in Bubnov-Galerkin we need to choose these weight functions as phi I, and for Petrov-Galerkin method we can choose arbitrary functions. This is my understanding of that question. So we can choose any function that lead to the system of linear equations. I believe I'm finished.
Yeah, yeah. Give me a minute. Yeah. Okay. Uh, yeah. You are correct. Let me iterate what you were trying to say. Uh, so normally, what Galerkin method requires is in the domain we orthogonalize in a weighted integral sense. We make the residue take it to 0. So this weight function can be arbitrarily chosen whatever we wish. So there are two things involved, like in the governing equation. Suppose I just use for bar E d square plus q equal to 0. This is my like a strong form. What do we have? What do we choose? Like first we take an approximate solution for u, and that is in terms of like phi, and that is incorporated in the residue. Residue will have this phi term, and we have now so one thing is like we have an option to select for phi, and second thing we have to select is this weight function v. What do we want to do? What do we normally do in Galerkin method? And the way we call Galerkin method, the standard Galerkin method is Bubnov-Galerkin method, and where we select this weight function equal to my approximation function. So this is just standard notation. We could select this weight function anything else also, but in the standard way, why to have a different, we can just uh, select the approximation function and weight function to be same. So this is not to be focused much more, just thing to remember. Okay, now let's move on to the next. Yeah, Rafael, you want to say something?
My question is here is we are choosing this function arbitrary,
Yeah.
but what is the requirements for these functions? So I'm just wondering, this function should about I wanted to ask about boundary conditions. What v is like a variation, so v should be zero on boundaries or what, or essential boundaries.
Yeah, so that depends on like what kind of our problem is. Suppose if our domain is also it's not restrictive, like it also changes, then this will also the boundaries for the weight function will also change accordingly. But that need to be said is I said that boundary conditions like V should satisfy homogeneous part of essential boundary conditions. Not all the boundary conditions, only essential boundary conditions are called as Dirichlet boundary conditions, if you know.
Yes. So v is always
This is for standard Galerkin method. So I have no not a like I'd say this is what is to be done in Galerkin method. Yeah.
okay. I just want to build a parallel um, between variational statement and weight statement. So I
Oh,
feel that
oh,
something is unclear here, because in variational sense we need to satisfy boundary conditions,
no.
but in
Yeah, yeah. I can say one thing is we just need to satisfy homogeneous boundary condition, and the way we select like for a bar problem, we have somewhere like EA du by dx. Suppose at x equal to L equal to some value q. So that is need to be need to be taken care by this uh, approximation function itself. I hope if I am not wrong.
okay,
And one more thing, like you said, what are the requirements? So first thing first is like this homogeneous part of essential boundary condition. Second thing is like our approximation solution, for a strong form, if our solution had to be exact, it had to satisfy C2 continuity. But when we transferred it to like weaker continuity sense, that u or approximation is like having C2 continuity or C1 continuity. If you are transferring that to my weight function, that weight function should also satisfy that continuity requirement, like C1 continuity or C2 continuity, whatever might be relevant to the problem.
Okay, thank you. I hope we can move on.
Yeah, okay. So next question is, let the governing differential equation is this uh, with boundary condition is u equal to 1 at x equal to 0 and u equal to 0 at x equal to 1. Consider u hat as one parameter approximate solution of u with this solution where phi naught is 1 minus x and phi 1 is x minus x square. C1 is coefficient in approximate solution. So if V is a weight function, the correct option for least squares method is. So I'll just solve this so that no problem will be there. So according to the question, we need to take one parameter approximate solution. Okay, Rafael wants to say something. Yeah.
Yes, we have already discussed this on forum, and this answers consist of error here.
Come again. I didn't get you.
The options that are presented here consist of error. Differentiation with respect to C1 was incorrect, and we have discussed already this on forum.
Okay, okay. You're saying about the discussion forum.
Yes,
Okay,
so this all variants here is erroneous. They
okay,
consist of error. Oh, I
okay.
believe we you can show right now here.
Yeah, yeah. Okay, okay. No problem. Yeah, I'll do that. So we have phi naught as 1 minus x, phi 1 as x minus x square. Okay. We have the governing equation as d square u by dx square plus u equal to 2 for the domain 0 x to 1. Okay. With boundary condition u at 0 is equal to 1 and u at 1 equal to 0. So what will be the residue pertaining to when we take an approximate? It will be equal to d square u hat by dx square plus u hat minus 2. Okay, so when we substitute u hat into this, we'll get d square c1 phi 1 plus phi naught by dx square plus c1 phi 1 plus phi naught minus 2. This can be simplified again as d square phi 1 by dx square plus d square phi naught dx square plus c1 phi 1 phi naught minus 2. Okay, we have phi naught as 1 minus x, phi 1 as x minus x square. So d phi naught by dx will be equal to minus 1 and d phi 1 by dx is equal to 1 minus 2x. Now substitute values in the equation of residue. R equal to C1. Okay. Uh,
We need to second derivative.
yeah. I got to this now. So d square phi, this will be minus 2 and d square phi naught by dx square is 0. So when substituted, this will be minus 2 plus d square phi naught is 0 plus c1. Phi 1 is x minus x square plus phi naught is 1 minus x minus 2 equal to 0. This will be minus 2 c1 plus c1x minus c1x square plus 1 minus x minus 2. Now arranging the equations, we'll have minus 2c1 minus 1, then c1x minus c1x square. Okay, So let's see. Okay. Okay, so there are no options here. Correct answer would be this.
No, no, we need to
Oh, okay.
we
Sorry.
need to
Take the derivative.
weight
Okay.
function, weight function.
Yeah. I'm sorry. So this is my residue. Okay. Now we need to find actually C1 value. The correct option. Sorry. For we need to find V, weight function, and weight function would be equal to taking derivative of R with respect to C1, and this will give me V is equal to minus 2 plus X minus 2 C1X. So minus 2, this will be X, and this will be equal to X square minus X square. So this will be my answer pertaining to my question. So minus 2 plus X minus X square. Okay, so here it should have been X square if it had been like minus X square. I would say this need not be the only solution. We could have taken other way also. Suppose if we had taken R uh, equal to, we took R as d square you had by dx square plus you had minus 2, right? What if we had taken minus of this? So that would have given me the answer. Uh, According to this will give me plus 2 minus x plus x square. Okay, so that is not much different, but just to give you one understanding. Okay, is this clear? Can we move on to the next question?
For me, it's clear. I don't know about this.
Abraham, can
Abraham.
we?
Yeah, we can move on.
Yeah, okay. Okay, next question is we have a governing differential equation as minus 3 second derivative of u equal to 5 for the domain 0 to 1 is subjected to the boundary condition, that is at 0 it's 1 and at 1 it's 0. Consider again u hat as a one parameter approximate solution with u hat as a c1 phi1 plus phi naught with phi naught as 1 minus x and phi1 as x times 1 minus x. Using Galerkin method, the coefficient c1 is. So like last time we were trying to solve, this is like similar way. I'll just again try to solve this without taking much time. So okay, we have u hat as c1 phi 1 plus phi naught, phi naught as 1 minus x and phi 1 as x times 1 minus x. Okay, we have governing differential equation as d square equal to 5 for 0x to 1 with boundary condition at 0 it's 1, u1 is 0. So residue would be what? Minus 3 d square u hat dx square minus 5, or we can take negative of this also, that is 3 d square u hat dx square plus 5. Okay, so that will give me 3 second derivative of okay, c1 phi 1 plus phi naught plus 5, this will be 3 c1 d square phi 1 dx square plus 3 d square phi naught by dx square plus 5. Now here d phi naught second derivative would be what? Minus 2, and second derivative of phi 1 would be what? Okay, so first derivative, wait, I should solve it step by step. So we have phi naught as 1 minus x square, phi. So d phi naught by dx would be minus 2x, and d square phi naught by dx square would be minus 2. Phi 1 is given as x times 1 minus x, right? This can be written as this. So first derivative of phi 1 would be 1 minus 2x, and second derivative of phi 1 would be minus 2. So it's coming out to be same. Now let's substitute this into the above equation. We'll have r as 3c1 d square phi 1 is minus 2 plus 3 minus 2 plus 5. This is equal to minus 6 c1 minus 6 plus 5, that is r is equal to minus 6 c1 minus 1. Okay, we need to find the coefficient c1. So in Galerkin method, what do we do is we have the domain, we multiply it with the weight function in the domain, and take the residue and making it in an integral sense equal to 0, and we have the parameter as phi 1 here, so we choose v is equal to phi 1 for the Galerkin method. So take v as phi 1, r is minus 6 c1 minus 1 dx equal to 0. So phi 1 is x 1 minus x minus x c1 minus 1 dx equal to 0. So this is equal to I can take minus 6 c1 minus 1 outside, and 0 to 1 x 1 minus x dx. Okay, could have just said c1 equal to 1 by 6, but it's better. I'll just solve like further. So 6 c1 plus 1, this will be equal to this is x times minus x square, x times minus x square dx equal to 0. So this is equal to x square by 2 minus x cube by 3, integrating on the domain. So 6 c1 plus 1, this is 1 by 2 minus 1 by 3 equal to 0. I don't know if it is correct. I have made somewhere mistake. I think 3 minus 2 1 by 6. This gives me c1 is equal to minus 1 by 6. Let me see. I think I should check.
The correct answer is 5 6.
5 by 6.
5 6. Yes. And can I? The first term should be 2c1 minus 5 in my solution. I believe the mistake is in residual.
Okay, let me see.
Sir, kindly show the last step. 6c1 plus 1 into 1 by 6 equal to 0. From that, 6c1 plus 1 equal to 6. It's just there.
No, but
And you will get 5 by 6 from there.
no. Here it won't give. I think
No,
somewhere
No, no,
residual.
no. Yes, yes, yes.
we have a mistake here, Abraham.
Let me check.
In residual.
Yeah, okay.
It should
Let
be
me
in
check.
residual.
So it's 3 d2u square plus 5. This is 3 times c1 d2 square, 3 d2 5. Okay, it's fine. Now phi naught. Okay, I just wrote this incorrect. This is 1 minus x. Yeah. So here we have made a mistake. So this would be minus 1. This would be 0. Okay. So this will give me here, it will be 0, and this will finally be 5 plus 5, so 61 plus 5. So that's why like if you write it plus 5 plus 5, even if we solve this thing, this part, plus 5, here it will be minus 5, minus 5, minus 5, minus 5. So this gives me C1 equal to 5 by 6. Okay, I hope that is rectified and the correct answer is 5 by 6. So moving on to the next question, if no problem is there, then can I?
I have no question.
Okay, sir.
Yeah, okay. So next question is similar. We have a governing differential equation given as this with the domain and the boundary conditions, and similarly 1 point approximate solution with phi naught this time as x and phi 1 as x times 1 minus x. Now this time we need to find the approximate solution using collocation method. So for this we'll just uh, substitute, like again we have c1 phi 1 plus phi naught as x, phi 1 as x times 1 minus x, that is x minus x square. Boundary condition as d by dx 2 plus x du by dx minus u equal to 3 for 0 to 1, 0 equal to 0, and u1 equal to 1. Now when we substitute this, we get the residue as d by dx 2 plus x. So this is in the for the whole domain, I think. Or this one, let me check it. Question, does it have some ambiguity?
I consider this as a ddx that acts to 2 plus x and also acts on du dx.
So this should be as in this, correct? Am I correct?
I consider this like
Okay.
as this.
As the question as this, okay.
But in solution we are given that it as if it ddx acts only du dx. It's erroneous solution again.
Yeah. Okay. Let's try both way, and let's find like what will be the solution respect to what differential equation. So suppose we take the question
Sorry, what is the second option for considering this ddx? Ambiguity. What's ambiguity here?
Yeah, actually, see, when I saw the question, d by dx, it's just showing 2 plus x du by dx minus u equal to 3. So when I see this, I thought d by dx first is acting on only on this. So there raises one thing. Either it should
I
have
believe
been.
it's silly to write like this.
Come again?
I believe it's a bit silly to
Yeah,
write like
yeah,
this.
yes, yes.
We can consider that 2 plus 6 is AE in our, for instance, in our bar equation. 2 plus 6
Mm.
is a function what is corresponding to AE.
Yeah, but what happens in, like, we take for a bar problem, we directly take d square u a dx
No, it's
square. So
this
the
is
in some question we have, like, if ea is a function, we also
yes,
take du by dx. This is like a more generalized
yes.
question.
So I believe that ddx is acting on both of them.
Yeah, yeah. The actually I also thought like it should act on both. Let's try both way. Let's see what solution we have pertaining to the respective, if we take the boundary condition as this, sorry, governing equation as this. So let's take case wise. This is case 1. When we take the differential acting on this both 2 plus x as well as du by dx. Okay, so with this we'll have a boundary sorry, differential equation. If we simplify it, we'll have it first acts on the 2 plus x by dx times du by dx plus 2 plus x d square u by dx square minus u equal to 3. Okay, and this will be equal to 1, so this will be du by dx and 2 plus x d square u by dx square minus u equal to 3. Okay, so for this my residue would be equal to what? 2 plus x d square u hat dx square plus du hat dx minus u hat minus 3. So 2 plus x double derivative dx square c1 phi 1 plus phi naught plus d by dx of c1 phi 1 plus phi naught minus uh, minus c1 phi 1 plus phi naught minus 3. Again solving it, we'll get c1 d2 phi 1 by dx square plus 2 plus x d2 phi naught by dx square plus c1 d phi 1 by dx plus d phi naught by dx minus c1 phi 1 minus phi naught minus 3. This is my residue. Okay. Uh, mm, okay. So, in what do we do in collocation method? So we have to solve this using collocation method and find the approximate solution. Okay, so before that, let's substitute what will be the second derivative. Okay, so first phi 1 is x minus x square and phi naught is x. So first derivative of phi 1 is 1 minus 2x. First derivative of phi naught is 1. Second derivative of phi 1 is minus 2 and second derivative of phi naught is 0. So let's substitute the values in R. We get R equal to 2 plus x c1 d square phi 1 minus this is minus 2, this is 0, so 0 plus c1 d phi 1 is 1 minus 2x plus phi d phi naught by dx is 1 minus c1 phi 1 is x minus x square minus phi naught is x and minus 3. So this is my residue. So what do we have in collocation method? We already have say u0 and 0 and u1 equal to 1. Say yeah. So we already have 2 points given. We just take one more point, say 1 by 2, and substitute this where like at these points my governing differential equation will be satisfied. So this at this point also that governing differential equation should satisfy, and if that is satisfying, this residue should come out to be 0. So what I am saying is we substitute r at x equal to 1 by 2 and that should give me 0. So if we substitute it, so that will be 2 plus 1 by 2 c1 minus 2 plus c1 1 minus 2 times 1 by 2 plus 1 minus c1 1 by 2 minus 1 by 2 square minus 1 by 2 minus 3 equal to 0. This can be simplified as 2 minus of 2 to the 4 5, this is 5 c1 and this will be 0, then plus 1 minus c1 1 by 2 minus 1 by 4, that will be 1 by 4, and this will be 1 by 2 minus 3 equal to 0. So again minus 5 c1, here 1 1 minus 3, that will be minus 2 and minus 1 by 2. Okay, c1 by 4, and we have minus 2 and 2 plus 1 by 2, that is 4 5 is 20 minus 21 by 4 c1, and this is 5 by 2. This will give me 5 2, that 10 by 21. So c1 comes out to be this. So with this for the with respect to this, my u is what, c1 phi 1 plus phi naught, so that is minus 10 by 21. Phi 1 is x times okay, x times 1 minus x, so this is x 1 minus x minus x square plus phi naught is x, I think yeah. So this gives me minus 10 by 21 x plus 10 by 21 x square plus x. So for with respect to this is my 10 by 21 x square, and 21 minus 10, that is 11 by 21 x. So approximately u is equal to, let me calculate it, 10 divided by 21, this is equal to 0.476 x square plus 0.524 x. This is when we take Gaussian differential equation as this. Okay, so does it matches with anyone? 0.476 x square, that does not matches with anyone. So let's try the second case which we wanted to take. So case 2, when we have our differential equation as we had d by dx of x plus 2 du by dx minus u equal to 3. So this is not the right way to write exact. It should be actually d2u by dx square minus u equal to 3. Okay, let's try this time with this thing. So residue would be for this would be x plus 2 t square. Yeah, Rafael, you want to say something?
I want to say that what are you trying to do now is written in our solution.
Okay, okay. So you already have
Do
the.
do we need to repeat that?
Okay,
I don't see the meaning. Yeah,
okay,
I consider.
okay, okay. So I think you have the solution, like the correct solution, like as the options are given.
Yes, they.
Options are given for this Gaussian differential equation, I think. Right.
Yes.
Okay, okay. So okay, I hope that is correct. Like you get what I wanted to say, that the question has some ambiguity. The question needs to be corrected and it should be written like this. I hope the, that is all right. Or if the question is like that only and the Gaussian differential equation is this, then the solution pertaining to that Gaussian differential equation would be this one. Okay, so I'll just move on to the next question. If Abraham also does not have any doubt further, can you confirm, Abraham? Yeah. Okay. Moving on. Uh, so next question is: let a cantilever bar is axially deformed with an axial load Q. The bar is discretized with 1D element where n1 and n2 are the safe function for node 1 and 2 respectively of each 1D bar element. L is length of each element. Axial displacement U is to be linear in axial coordinate x if each element is approximated with a linear polynomial. The correct option is, I think you guys already know the answers. uh, you can just confirm soon. Anyway,
I know the answer.
yeah, uh, you can say.
Is the first one.
Yeah, okay. I don't think if there is a need to explain it further. If anyone wants to know, then I can, or otherwise I'll move on to the next question. uh, okay, moving on to the next
I'm
question.
not sure for Abraham, but I want to move on.
Okay, moving on to the next question. This is a question. This is a cantilever stepped bar made of two different materials, M1 and M2. The bar is subjected to an axial load of 50 kN at its free end. A1 is having area as 78 mm square. Second material is having area as 20 mm square. Young's modulus for the first material is 78 GPa and second material is having 210 GPa. So, and length of the both materials are 5 mm each. We need to find the displacement at node 2. So, I think you guys know, but I'll just do this quickly. So, for a bar element, what do we have? An element stiffness matrix as AE by L 1 minus 1 minus 1 1. This is like okay. So if I take my first element, so this will be with respect to what, u1 u2 u1 u2. I better draw the diagram also so that you guys don't get confused. So we have two bars, load is applied here, 50 kilonewton. Okay, A1 E1 L1 A2 E2 L2. We have the name as 1 2 3. So I'm taking the degree of freedom as u1 here, u2 here, and u3 here. So for the first element, this will element stiffness matrix will have as A1 E1 upon L1 1 minus 1, and for the second element we have stiffness matrix as A2 E2 upon L2 1 minus 1 minus 1 1, and this is with respect to u2 u2 u3. Okay, so when we assemble these two element stiffness matrix to get the global stiffness matrix, we'll have what, if I take u1 u2 u3 u1 u2 u3. So with that we'll have what here, A1 E1 upon L1. This will be minus A1 E1 L1. Let me first write it. This will be equal to minus A1 E1 L1, and this will be A1 E1 L1. Now when we add the second stiffness matrix to the global, we'll get this as so this will be E2 E2 L2 minus E2 E2 L2 minus E2 E2 L2, and this will be E2 E2 L2. So left with this will be 0, this will be 0. So substituting the values, we'll have this. We have A1 as 78, A1 as 78, A2 as 20, E1 as 78, E2 as 210, L1 and L2 equal to 5. These are mm square, GPa, and this is 5 mm. Right. Okay, substituting this, so I better we have prominently through two values. We have a1 e1 upon l1, that is equal to 78. e1 is 78, l1 is 5. So let's say what is that equal to, that is equal to 1216. So this is 10 power 6 MPa, Newton per mm square, and 3. So 1216.8 into 10 power 3 Newton per mm. Similarly for E2, L2 will be equal to, so this is 20, 210 upon 5. This is equal to 840 into 10 power 3 Newton per mm. Or we can just write it as kilonewton per mm. 840 kilonewton per mm. So Kg will be equal to 1216.8 minus 1216.8 minus 1216.8. This will be equal to 2056.8 minus 840 minus 840 plus 840, 0. Now we need to find the value of u2. Question asked is to find u2. So we have the force relation as, we know the force relation will be what, kg times u is equal to force, right, where kg is my global stiffness matrix, which is as found earlier, minus 1216.8 minus 1216.8. This is 2056.8 minus 840, 0. So u includes my displacement value. So this is like for u1, u2, u3, and correspondingly what will be my force at those nodes. So suppose I take force at nodes as r1, r2, r3. Okay, so as you see, question pertaining to my problem is, this is at node 1, 2, 3. So we have at node 1 equal to 0, that is u1 would be 0, and we have what do you say, the force applied at node 2 is nothing, so that is also 0. So that will give me r2 as 0, and sorry, this is force applied at node 2, I should write it better as F, I was saying, and F at node 3 is equal to what, this given as 50 kilonewton, if I'm not wrong. Yes, so R3 is equal to 50. So when we substitute into the above equation, 1216.8 minus 1216.8, this is 2056.8, 840 minus 840, and this is 840 minus 1216, 0. So this is what, 0, u2, u3 are unknowns. R1 will be unknown as we don't know the reaction there, and R2 is 0 and R3 is 50. So we have known values in the right hand side as these two values, and respectively we have unknown values u2, u3. So with that, when we reduce it, this stiffness matrix, like sorry, yeah. So like we'll just reduce this stiffness matrix pertaining to only this known values. So yeah, we'll just want to take the second equation and third equation. So let's take it. Uh, so if we take the second equation, we'll have what? 1216.8 times 0 plus 2056.8 u2 minus 840 u3 is equal to 0, and 0 times 8 minus 840 u2 plus 840 u3 is equal to 50. So these are my two equations. Solving these two equations will give our u2. So from the first equation, suppose A, this is B. From A we have our u3 as 2056.8 u2 upon 840. Substitute into B. This is equal to minus 840 u2 plus 840 u3 is 2056.8 u2 upon 840 equal to 50. So let's simplify it quickly. This will be 2056.8 u2 equal to minus 840 divided by 50. So this will be 1216.8 u2 equal to 50, and u2 will be equal to 50 upon 1216.8. This is equal to 0.0411 mm. So this can be approximately written as 0.04 mm. So this is the correct answer. The correct answer is option B. Okay, and I hope no problem is there in the explanation. So I'll just ask the last question and then we'll move on, like if anybody has doubt anywhere. So last question for today's session is: in finite element method, at a node of interest in a body, summation of all the shape function is. So answer is B. Yeah, answer is 1. So that concludes what the discussion of assignment questions. So if anybody has, first of all I'll ask, like if anybody has doubt in the questions discussed, then we can discuss that first, and then if any other thing we have to discuss, we'll discuss that. So anyone has discussed regarding today's session as of now? Rafael?
What? For today's session, it is just a solution of a quiz. I was quite successful on this quiz, and each problem, I believe,
Yeah,
absolutely clear.
yeah, okay. Abraham? Abraham? Yeah, okay. So, anybody, like, apart from this, what do you guys have any doubt? Phil was
Yes, I
saying,
have. Questions regarding the lecture material.
yeah, okay. Tell me, I'll just look into it.
Can I share my screen?
Yeah, sure. I'll just stop sharing mine. Just give me a minute. Okay, go ahead.
Uh, in lecture material, when we derive weak form for a question for bar element, weak form of bar element.
Yeah,
I
okay.
have two questions. One theoretical, I feel philosophical, I believe, not theoretical. And the second is technical. I wanted to first ask about the philosophical question: why we are trying to write our approximation in this way? Because it's not in a Galerkin way of approximate function. It's not a Rayleigh-Ritz method, because our phi I is not satisfy boundary conditions here, or they are satisfied here. When we take this approximation, our phi is not
Uh,
satisfying conditions in an elemental equation. I believe when consider one element.
okay.
This is a philosophical question.
Uh, can you just again go back to what you were sharing earlier?
Uh, e- Eller, Eller. It's about the question slides on the lecture, or
Because
look here. Let me show you my trouble. This trouble I ask because this trouble repeats again and again. And look, this one, elemental equation. Where it is? This this part is not clear.
can you zoom in a bit?
When we yes,
Yeah, okay.
when we consider elemental equation, when we write a weak form for the element equation,
Mm,
it's not clear about this part. Uh, where phi I qi presented. We have a what I wanted to ask when we have elemental equation, we have a, for instance, when we have elemental equation, we have a stress in the element. I believe stress in the element, internal force. We have external force here, Q1 and Q2, as it refer in lectures, as it called in lectures, and we have a U1, U2. I wanted to ask about this Q1 and Q2 because when we approach this directly, we call it phi1 element and phi f1, f2 element. And I wanted to ask how work with Q1 and Q2 here, because I repeat the derivation of the elemental equation, and I cannot come up with this part. So I don't understand what's going on here in this bracket.
so, first thing first, like uh, Galerkin method depends on the choose. First, we choose weight function. Like how we choose our weight function, that is like our most important criteria, and that is like we choose the shape function. Shape functions depends on what kind of approximation we want to take. Suppose if you take an element as a linear element, as you are showing just now, so we suppose we take a single element and we take a single element and the nodes are there at the end. So we just we tell that we assume there's a linear approximation in between the element. So uh, I'll just try to
Could you share
explain.
screen again, please?
Yeah. Let me. Uh, uh, is it visible?
Yes.
Yeah. So what I am saying is, uh, okay. So you asked. Let me confirm that what you are trying to ask is, suppose we have first element or second element, node 1, 2. This is 1, 2. Like for the first element, node 1, it's 2. So mm, we have an element stiffness matrix. For that, we have U1, U2, right? This is having something like if external forces are applied here, F1, F2, this is subtracted with some internal forces. How is this internal forces coming up? I think you want to ask that thing uh, in an element wise sense.
Uh, F1, F2 is
External,
forces that come out from uh, Q, distributed load. This
externally applied load. That's right.
yes, this one, the last part of your bracket, it
Yeah,
is
internal
uh,
force.
it's not like internal force. It's like a force on a boundary of this element.
Yeah, like
I believe I understand like that. Be-
uh,
be-
whatever forces, uh, the use of the node says that when we use displacement based approach, whatever computation we do at the node. So even if forces are there in between the element, like even
this absolutely clear. This is absolutely clear.
util is there, we distribute the
All
loads at.
forces should be on the node. It's clear.
Yeah. So this thing comes due to internal force. Like as there was a question earlier, this was our problem, right? This was our problem. I took node 1, 2, 3. I wrote kg times u equal to f. This f includes both external as well as internal, as in uh, as in u1, u2, u3. Here we don't have any issue. Suppose if we take the first element here, first element k element 1, u1, u2. If you
Uh,
are saying, suppose there was a UDL here, forces were equally distributed and we got F1, F2 at the nodes, minus why we have this, right? This is due to when we restrict this, like this element 1 has a restriction at node 1, right? This element 1 has a restriction at node 1, so that will develop an internal force in the system. And if you see in the context of my boundary conditions, like okay, uh, uh, let me generate the space. I'll just try to explain. So for a bar problem, we had this Koenig differential equation.
you
Uh,
are consider sorry, this equation you consider for the whole domain or for the elemental domain?
Yeah,
Because
I'm
my
just
question is about weak
element
form
element.
or element. Yes.
Yes. I'm just
Okay.
getting into those things. So, if I see as my whole domain, this was something like this. U at L at sorry, we had E A du by dx at L equal to something force. Okay, this was given. Now for when we get into an element perspective, that boundary condition is still need to be satisfied. Sorry, uh, what? How should I say? Uh,
I believe that
this,
this boundary condition also should be satisfied.
huh. So this uh, is still there. So uh, how should I say this? Let me say. Mm, 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 mm. Okay.
I believe you want to say that this can after all
Let me.
after assembling this condition will be satisfied. I
Yeah,
believe it's true.
I'll just try to solve this other way so that you guys don't have any issues. So suppose how do we get the this? Finally, we solve this boundary condition. Sorry, this algebraic equation, right? So how do we get that? So, so first of all, we have this governing differential equation. This is applicable for throughout the domain, and we have some boundary conditions. Say this and EA du by dx at L equal to some p. So say, and what do is we multiply with the weight function throughout the domain, right? And then we convert this into. So what I can think of as of now is, see, this uh, is what we are integrating throughout the domain. Like we are integrating in an integral sense, but in finite element, what do? We take an element-wise integration, right? So rather, like if I'll integrate this thing in first element, the same E a d square u dx square plus q dx plus in the second element, same thing E a d square u dx square plus q dx equal to 0, right? And this element 1 has suppose domain as 0 to L by 2 V a d square u dx square plus q dx plus L by 2 to L V e a d square u dx plus q dx equal to 0. Now, if you see, like as a whole, when we as a whole solve for this, we get some kd is equal to f, right? This is when we take in a global sense. Now, when we are solving in an element wise, there also we are getting some element. I hope you're getting my point. One, 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 one. Sorry, this is for second. So what I'm saying is you were asking how these internal forces came into existence. So if you see, like mm, here we get the boundaries at what? At 0 and at L by 2. Boundary will be sometimes pertaining to at the boundaries 0 and L by 2 for this element, and for this element it will be at L by 2 and V0. When I wrote everything, when I wrote it collectively, I just wrote R1 and nothing like that. What will happen is for internal forces for the middle node, it will just cancel it out. As you see, this is for the upper limit, this is for the lower limit. So it will be having some like term like it will be like dv by dx, something du by dx at L by 2 minus at 0, and this will be having some uh, at L minus at L by 2. So if you see this and this, cancel it out, right? So we are left with again the boundary terms pertaining to the boundaries. I hope that is giving some insight regarding that internal.
Thank you. I believe that they are canceling out, but now I wanted just to show prof as professor did, and I failed with that. Could you please again look at my screen, please?
Yeah. Okay. Let me stop sharing first. Yeah.
I believe I showed you the wrong slide. Now it's correct. Can you see the screen?
No, not yet.
This one. I believe that I need to just ensure that it is happening. This what you've said.
Yeah. This is what
I want to see that in my equations, but it doesn't happen by some way. I believe there is something missed here.
Okay,
So can you see this elemental weak form? Can you see the screen?
yes, I can see. You just wrote D by.
Look. This is clear.
Oh,
For I21, this is clear. The weak form is clear. This is clear. This is clear. Minus phi I xi ae du per dx at x1 is not clear. Could you please?
Can you please repeat once again the last statement which you said?
This they are on another.
Just give me.
They colored here.
Yeah. Can you repeat once again? I was something.
This colored thing is not clear.
Minus phi I x1 ae
Yes.
du by dx at x equal to
Yes.
x1 plus n. Yeah.
Could you please first say to me ae du per dx is what? It is a
boundary term.
It's a boundary term. It is a projection of this. Look, I just if we consider strength of material, if we consider strength of material thing, yeah, and consider a bar in equilibrium.
Yeah.
Look,
Okay.
if we're considering bar in equilibrium, for instance, I don't know, this is a cantilever beam. This is a force, and we consider what is going on here, for instance, on this section. And this section is in equilibrium. So internal force is equal to F. So this internal force, they are equal to each other and they are equal to F. But what in elemental, what show this boundary term in element? It is a show our internal force, or it is just a force in this, it is a force on this point. I don't understand that. EA du dx is showing me F or an internal force. If it is internal force, it should be positive. If it is a projection of the force on X, it should be negative. I don't know. I don't understand why minus coming up here. I don't understand this minus. For instance, in ready book, I see this. I see this in my element du dx.
So, okay, are you confused? Like, are you asking about the why that's a negative, why that's a positive, or something like that? If I
Yes, this details is not clear because I don't know what is this. What does this mean in the elemental sense? Because as I can in strength of material, I can show this as a force as a look. Do you agree that this n is positive here? Because internal force positive when we have elongation. Is that okay?
see what professor is showing actually and what is writing in that
Yes.
it's a different thing. I'll just share mine and then
Okay.
I'll just try to
I
explain
hope you
further.
understand my
Yeah, yeah.
no.
If I don't get it, you can just again
Okay.
ask in
Thanks.
between. Okay, let me try to finite element method. This is which
Sorry,
lecture?
I don't see the screen.
No, no, I'm just asking first. Which week's lecture is this?
This week, so week 3.
Week three. Okay.
The slide number 26.
Okay. Just a minute. Is my screen visible?
Yes.
26, you said. Yeah. Okay. So, do you have doubt in this? Like, till this point, you are clear, right?
Actually, yeah, yes, yes. Uh, Actually, I don't know. This is a small point. I don't want to talk about this small point, which is unclear. I want to talk about the first point about sign. Let's talk about sign Q1 and
No,
Q2,
no, no.
which is
I want to take it step by step. Like, if you are okay with this thing first.
oh, okay. This is I don't know why we just took dudx here. From my perspective, we need to work further with F1 element and F2 element. I don't know why the professor collect this into dudx. This is my small point. So after integration by parts, we need to obtain the following. If we proceed, we should obtain phi I at x1
Uh,
and ae d phi 1 element or
mm.
multiplied by u1 element. I believe it should be correct, but professor collected here into du dx. I don't know why. Uh,
Actually, I'm still not able to understand your question. I'll just
okay, I believe
see.
you understand my question with about the sign of the Q at least.
Aha. So this like for finite element method, what do we do is we assume a particular sign convention. Like u1 is along this direction. Like it will be for this direction for all throughout the element. Like in strength of material, we what do we do? Like if I remember it correctly, for sagging moment we take a positive sign convention when we
Yes.
from the left hand side it's sorry, it's clockwise, and from the right hand side if it's counterclockwise, then we take it as a positive sign. But
Yes.
this is not the case. This is for strength of material, but in finite element method we choose a particular sign, and that will be for all. Like if we are taking positive sign for this will be the same for all. We should not change at every point. So uh, what I can understand from this is in FEM normally we take this side as my positive sign convention. Okay.
Okay. Okay.
So even though he's showing like this, in reality, like uh, in FEM convention, it's Q2 this side, Q1 this side.
Okay. But professor, by some reason, directed Q1 negative. I don't
Yeah,
know
I
why.
think he didn't think in the sign convention perspective. He just wrote it in a sense like if you see a force both on the right side, uh, students will think like body will try to move only on the right side. But if
Okay.
forces are there on the both side, then some thing will be going on. So this is I think this is in the context of FEM. The Q1 and Q2 both will be in the same direction. I hope that solves some of your doubt, I suppose.
Yes, if you say that it is a convention, but now, if it is a convention, could you please, what, do you know this formula EA du dx is equal to minus traction, minus traction
Yes, EA du by dx
is equal to
is
minus traction. Do you know
okay.
this formula?
Okay. So
Can you please? It might be this is going on, or this something is going on with respect to traction, because strength of material in my course of strength of material does not consider traction at all. So I believe it's in following courses like
see,
theory of elasticity.
okay, I'll just if you have studied solid mechanics, then traction is sigma acting on normal.
Yes.
Okay, so for a bar problem, it's just sigma 1 1, and okay, suppose in the
Look,
bar
at least with the minus traction, it corresponds to the Q here. So if we consider this formula and consider like a minus traction, I believe it should be correct here.
yeah, yes, actually this is the traction itself, like in the boundary condition when you
So boundary condition
when
should, yeah.
when you are provided with the governing equation, sorry, strong form, what do you have? Governing equation and boundary condition, and boundary condition should have, like, this is for a bar problem, so one boundary condition would be Dirichlet boundary condition and one boundary condition would be Neumann boundary condition or natural boundary condition. So suppose u0 equal to 0 and uh, we have what, Ea du by dx at L equal to some force or something like this. So this is like what a Neumann boundary condition, and this is what, this is actually traction itself or stress. So
Okay.
so this is like for the whole domain we are saying we are given at the endpoints. We have the boundaries, like we have as a whole domain, then we are having only two boundaries, right? Boundary points. And
Yes.
when we are taking an element will be having boundaries differently. This, right? With respect to that, we'll have these boundary terms. And when we collectively add those both, it get cancelled, it gets nullified, and uh, uh, the internal force existing, like pertaining to my Dirichlet condition, that only remains. And for the normal boundary condition pertaining to what the problem has already given, we have to substitute that itself.
Okay. I need to sleep with this, I believe.
This part you are getting is, this is actually the stress itself, right? This is the traction.
Look, I don't understand. I don't understand. I feel that I something missed here from in the mechanical sense because EA du dx is the force if we consider this term.
Yes,
But
yes, yes.
I don't understand. This should be in infinite element method. It should show me internal force at point,
See,
like in stable material, or just force and external. It can this term consider is that external term or as in
no, no,
internal.
no. It's actually internal force. Just see, EA du by dx is what? This is a force, right? But this force should
Sorry.
EA du by dx term is a force. Uh, is a type of force. You can agree there, right? Now,
Look, in strength of material, we have an internal force from which we can obtain stress. Okay,
yeah.
but this finite element method consider this as an external term. This is a point I miss here.
See,
And
again, see the external forces where the forces are applied. That is, that comes from this part. These are internal force. I beg to differ.
okay, this is okay, okay.
So say, don't think it in that context. If you are confused there, you can think in this perspective also. Like, don't think differently like external forces or internal forces. We just need to distribute all the forces into the different nodes.
Could you please repeat again?
Okay. Let
Don't
me draw.
think this as an external and internal or
Let me draw this element. Okay. We have first element, second element. Node 1, 2, 3. Okay. We have applied externally applied force is suppose here, here both P1, P2.
yes. This is
Okay.
external applied force. I
Yeah.
agree with definition.
Now, when
Could you
we
please consider in this problem element until elemental force?
yeah, I'm trying to. I was
Yes.
going into that. So first, when we draw an element, when we draw the element, first of all, what we have done is we remove this boundary condition itself,
Yes.
right?
Yes.
So when we have see earlier there was a restriction to this. So when we are freeing that body, uh, first of all, like if I draw all the elements, okay. Now, if I just only draw the external forces, okay. So here there was no external forces. Here
Yes.
there was P1. Here there was a P1. Here there was a P2, right?
Yes. Yes.
But
Yes.
when we divide this P1 into the both elements, this will be like P1 by 2, P1 by 2, right? We divide it equally if the elements are having same length and materials, okay. Now, initially, this first element was restrictive in the sense this cannot, node 1 cannot move. Node 1 cannot move, and we have not applied any force over there. Uh, we have not applied any force there, but forces are applied here. But so there is a chance that it should move on the right side, right? If I see only this thing, so what should this imply? That body will move on the right side. But we know that there is a restriction on this node. This is not moving. So this should what should be there? Some internal forces should be there here. Then only this thing can be restricted, or this could be uh, like displacement will be equal to 0 here. So say, suppose internal forces are here also, here also, here also. But what will happen in the mid nodes? They cancel each other. Like if it is plus here, here it's minus. It's equal and opposite. Here also it remains.
Okay, I need to.
So these things are actually what is coming here. This AE du by dx at x equal to 1. Like these internal forces, it's coming, right? My phi I, it's shown phi I x1 AE du by dx at x equal to x1 plus phi I x2 AE du by dx x equal to s2, right? So this is how is it coming? This is coming from, like, if you are taking x1 here, this is when we are taking s2 here, and this is in plus limit. Why? Because it's in the upper bound, and this is in minus because it's in the lower bound.
Okay. Okay, it's difficult even in bar element. So what
So,
we can
so
say
in the beam,
in a beam? Yes, it's
so in the beam element, if I tell you, like, as the bar was restricted in the movement of u1, so the conjugate part for u1 is what, force,
force.
or
Yes.
so when the beam is there, uh, this is fixed beam,
Yeah.
if I say.
Yes.
So when we are restricting here, uh, so uh, when we are restricting u as 0 and slope as 0, right? So for this, my shear would be 0 and my moment would be equal to 0. Sorry, unknown should be non-zero, and this should be non-zero when we remove this thing
Yes.
as an internal thing. So what will have as E, there it comes like EI d cube W by dx cube, something like this form. Sorry, and d2W by dx square. So uh,
And they
uh,
consider with respect to again finite element consider all vertices. They
yes,
also will be positive on the node.
yes, yes. So you cannot in between change your sign convention. The sign convention should be uniformly for everything. Like if you are taking right, this as your convention, it should be for all the elements throughout the body. If you are following this, it should be for all the elements, because your governing equation will change accordingly. Because if you see, if you take this, but in the strength of material, uh, what do you take?
The
This
strength the problem with the strength of material is that in strength of material in this picture shows us internal force, not external force. Look, it's
yes
not a boundary term. It shows
is
internal force.
reaction. Yeah.
Yeah.
Yes.
Yeah. And
So
from my perspective, du dx multiplied by EA should show me internal force in this point. But by some reason, finite element method says me it's external. I don't get it at the moment. I don't understand this. It's difficult to me to explain.
I just say one thing. You don't uh, think internal force, or just see it as a something called a force quantity.
Okay.
Don't
Don't over
see,
how to say that.
like let me, I solved one question, right? Here, see, I solved. I took R1, R2, R3 here in the first value.
No, look at this level. When we consider this problem, I understand everything because I know that R1 is reaction, R2 is a free node. There is no force is equal. R3 is a force external. But how it's how to prove that mathematically? I this in this case I have some kind of
Doubt.
difficulties.
No,
Yes,
so
and you know what? These difficulties on the bar level is okay, but these difficulties repeat again and again in more complex subject, in more complex topics like two-dimensional temperature problem and
see,
of course stress problem in elasticity 2D.
what I think is I don't like uh, for my simplicity, I don't consider like internal force or external force. I see them both as a forces, and they have some magnitude and signs. Like if external forces are applied in this direction and internal forces are this direction, I have to just sum it up, and that will be my R1, R2, R3.
Okay.
So
Can you please open the lecture one slides at the page? At the
lecture.
page, I will ask. I will say you in a second. Looks no, it is not on slides because he derived it by hand. Can I look at lectures? Right now? It is a it is a slide number 30.
30.
Lecture week one.
Yeah, this
And
is.
I just look at the lecture inside. It is in the video. Professor derived that.
I don't know. Is this not the one? The
Yes. Please wait a minute. I will try to look inside the lecture. Look, yes, I found that. It is 26 minutes on the lecture 3.
you want lecture 3 material, right? Or lecture 1?
No,
Week 1.
lecture 3, week 1, lecture 3, 26 minutes. He
Oh,
just use his pencil and he writes this, but handwriting is not on
okay.
slides.
It's best like if you can share your screen so that I
Okay.
can.
Can you see?
Yeah.
Look, professor here is look inside the element and he divide the element as we do that in strength of material. Look, this is the internal force. Phi and phi one element, phi two element. This is internal force, but in order to consider equilibrium, he divide this and
Yeah.
he use this internal force. He is directing internal force as we did in strength of material.
Yeah.
So they are directed in the right way. But you know this from the strength of material, P1 is equal to EA du dx. So from my perspective, we cannot consider this term as a boundary term. I don't know why finite element method uses actually. I think that I missed something here. I don't understand what is the reason. So in the point 1, du dx over EA is equal to internal force. I mean internal, like the force that can be derived from stress. You know, it's like the first the hypothesis of strength of material.
Mm,
Okay, thank you for the discussion. I believe I need to
well,
go
look,
deeper and look again at this
if you
with what you said.
I still don't understand like what is like only the negative sign is troubling you, right? Or
I
as a
believe that
or the conceptual thing, because in the
conceptual thing. You said me one conceptual thing, and it will be a foundation of my dopes when I consider this again. You said that in the finite element method, uh,
the
we
sign
choose sign
convention.
convention and we use it as a boundary term. Now I need to understand what does it mean mechanically.
Yeah.
Because now I need to understand it. But I believe I should do it in myself because
See,
it is not your problem.
uh, if you see the slide also, like week 3 lecture, which you were showing earlier,
Okay.
you can open the lecture, week 3 lecture.
Yes. Yes.
No, sorry, week 1 lecture.
Week one lecture slides. Okay.
Yeah. So this is simply see F11 is like F12, F12, like F21. F1, F2, F3 are is like my net force. So don't get
Small
confused.
f, small f. Yes. This is a net force.
Yeah.
They, yes, I
So
agree with that.
so don't think too much. Actually, I would say.
Okay. But I try to think too much because these
Uh,
things
see.
are show themselves in more and more complex topics in
Okay,
finite
so
element.
I'll ask you one thing. Like if you're still having doubt, you better write it properly. Like if you're having doubt in a beam problem, also the same internal boundary conditions, something like that. You better formulate it and send it in the discussion forum. We can discuss over there also, or
Did
else.
you see the discussion forum? Honestly, say it to me.
No,
The discussion forum is absolutely.
actually, those things
Look,
are.
when I try to ask my question in discussion forum, they say to me, they send to me to the books. They don't answer me questions.
Uh, those things are actually answered by a third person, so I don't. So
Okay,
but I
so
feel, when I feel like there are some genuine questions, I do feel like I should explore those and try to answer those things. But I find it questions like what you posted where uh, regarding the discussion sessions to be organized, like one discussion session should have been organized during Tuesdays or Mondays. I don't remember properly. That should have been organized by a different person, and I think he has quit this thing. So I'm only dealing with that. So only on Saturdays, 3 to 5 only we can meet. That's our timeline actually. So
okay.
it's not proper to just argue everyone. That's how I would say. You better post your question. Uh, if I feel I can give your answer, I'll try to post it.
I'm not trying to argue, but I consider my questions as not like silly questions that I
Yeah,
can
yeah,
easily find in the
I got.
internet. You know,
I got one thing that you want to get into the internal force. How is that coming up? Is it like minus, or how, is it coming with my sign convention automatically? You want to confirm. So
yes,
I'll
I
just
want to
ask you.
confirm.
We have this bar problem, right? Better formulate your question for the bar problem as well as for the beam problem and see the difference. How is it coming up? If you can do that and post it. or else we can have it on the next discussion session as well, if you don't mind.
Okay. Okay. Thank you for the session.
Yeah,
If we have a 1 minute, I will try to find this on ReadyBook.
yeah, okay, come on.
Here, I just try to find this. As I understood, the TA responsible for the discussion forum, the TA responsible for the sessions, they
Different,
are
yeah.
different persons at all. So,
Yes, yes. Yeah.
by the way, there were no discussion session on the assigned time previous week.
No, on
No,
Saturday.
Monday
Yeah,
session.
I
Sorry.
think I am not sure, but I think the person. Yeah, Abdullah, you want to say something?
No, no, actually, I'm just listening. Thank you.
Okay, okay. So to make it clear, that session would have like that was to be organized by a different TA, and the discussion session would be for the week 3 or week 2, same thing which we discussed, but that would have been organized by a different TA. But I think that assigned person has quit. He has not taken up the task. That's why it has been cancelled.
Okay.
So you better
I am
come.
sharing my.
Yeah, okay.
I'm sharing on my
Screen. Yeah, I can see.
screen. Look. What's going on? This is going on also in ReadyBook.
Actually, you're sharing your browser. You should share your PDF.
Oh,
What is?
sorry. Is it visible?
Yeah. You're showing slides, right?
No, I'm sharing. Okay, I believe I choose the screen sharing, but by some reason it chooses browser.
No, you.
Sorry.
There should come an option. If you are using two screen, there should come an option to select which screen to. Yeah. Yeah, yeah. Now it's showing.
Look, do you see that they put minus here by some reason? It's
Okay.
also interesting. The second condition that they use in the bar is a minus sign again. But if we look at the element, they will direct Q as a positive Q. Look. Now I will try to where it is. You see that our Q here is positive.
Yeah, so this actually makes my point clear actually. So, uh, as I told you, a sign convention should be only in the one direction, right?
Yes.
Yes. Now this
Yes.
Q2 value, if you see, it should be it's exactly this a du by dx. But
Yes.
for Q1, it should in reality it is opposing the reaction. It should be in the negative side, right? But our sign convention is to take everything along the positive side. That's why we are taking minus a du by dx at the left hand side.
Sorry.
If you see the derivation of a beam element, I think that has been.
Yes.
So there you must have seen that at the left nodes. I'll just share my screen if you can like.
Yes.
So in okay, you can see my screen. So
Yes.
normally this is what is there in the SOM, if I'm correct, right? Strength of material. This is the sign convention.
No.
Okay. Sorry. This is sorry.
This is it. Yes.
Yeah. But in FEM, we take uh, this, and this. Okay.
Okay.
So normally, how do we find
You look.
EI D2?
You know what? In this, uh, as finite element method is a mathematical method, I believe that this sign convention should correspond to the equation they wrote. So
No, see, FEM method is a numerical method that has been
yes.
developed to ease our problem. Strength of material is a conceptual thing. So,
Okay.
so like uh, uh, equation wise, like what is my moment? It is EI d2y by dx square. In a general sense, V is what? EI d cube y by dx cube, right?
Yes. Yes.
This is, if we use this, we we use this for all like this equation we apply, whatever we wherever we apply, this will be applicable for all, right?
Yes.
I mean to
Because
say,
because because m of x and v of x, it is a, moment, internal moment, and v it is a shear force at that particular point. It is internal moment at that particular point.
yeah.
Uh, if we choose the point in the element, we can find an internal moment. From this, we can find a stress or other thing
So
in strength moment. But infinite element method,
so what do we
we
do in
use the same.
we use this equation, like we use this equation if we are following the sign convention. So if we use the same convention, like if we write v1 m1, if we write v2 m2, so for v1 we will use the same equation d cube y by dx cube, where x is equal to x1, m1 is ei d2y by dx square, where my x equal to x1. But for v2, what will have? See, uh, this is v2 and this v2 are having a different sign convention. So uh, ei d q y by dx cube, this would have been with respect to strength of material. But to get the same sign convention thing going on, we take minus here. Likewise for M2, we take minus EI d2y by dx square is equal to x2. So,
Okay.
so when you arrange all, like uh, for all these four, uh, we get the like we get four equation in terms of, like if you are taking displacement as d1, or let me say this is like this is I'm taking this is as v1, this is as phi1, and this is as v2, this is as phi2, like my degree of freedom. So when we expand this all four equation, we will have four equation in terms of v1 phi1 v2 phi2 respectively. We will have what? v1 m1 v2 m2. So this global stiffness matrix is actually considering those this sign convention also.
Okay.
So better go through this once again, so that
Yes, I will try.
yeah.
Thanks.
Yeah, okay.
I believe it was not so boring for you to explain that things.
No problem.
Okay.
I hope that actually some insight. If I'm not able to solve it
Yes.
out completely, some insight so that you can think
Yes.
of and maybe later on ask again.
I will ask.
Yeah. Okay.
Okay, thanks for the session.
Yeah. Okay. We are ending the session now. Hope to meet you on the next weekend. Have a nice weekend.
Have a nice weekend.
Yeah. Bye. Take care.